Okay, let's continue from block number E. And the eigenvalues of that. So then the characteristic polynomial can be formed by getting the determinant of 2 minus lambda, and then all these are 0. Then -1, 1 minus lambda, all these are zeros. And then 3, and then -1 here, and then 0 minus lambda. So it is minus lambda, and then 0, 0. Then we have 5, 4, -3, 2 minus lambda, and then 0. And then we have 0, -3, 0, -2, 3 minus lambda. So we want to get a determinant. Now, since it is angular matrix, then we just multiply the leading over the main diagonal. So our characteristic polynomial will now be equals to 2 minus lambda, 1 minus lambda, minus lambda, 2 minus lambda, 3 minus lambda, 3 minus lambda. So since this is a 1, 2, 3, 4, 5, so this is our 5 by 5 matrix. So basically, this is of degree 5. So degree 5. So our characteristic polynomial is equals to negative lambda raised to 5 plus 8 lambda raised to 4 minus 23 lambda raised to 3 plus 28 lambda square minus 12. So that is our characteristic polynomial. So what is the characteristic equation? So you just equate this one to 0. So our lambda equals to 0 equals to 2 minus lambda, 1 minus lambda, minus lambda, 2 minus lambda, and then 3 minus lambda. Now, using the zero product property, then 2 minus lambda equals to 0, 1 minus lambda equals to 0, minus lambda equals to 0, 2 minus lambda equals to 0, and then 3 minus lambda equals to 0. So finally, the eigen values of A are, so you can start from the smallest. So we have lambda equals to 0, lambda equals to 0. The next one here is lambda equals to 1. So we can say this is lambda 1, and this is lambda 2. And then our lambda 3 is when lambda equals to 2. So we have 1, and then we have another one. So lambda equals to 2 with multiplicities. So you can say multiplicity 2 with multiplicity 2. So there are 2 of them. So lambda 3 are 2. And then finally, our lambda 4 equals to 3.
How did you want to subtract lambda across the It's not plus.
This one.
Yeah, how did you know that you subtract lambda across all?
So using the formula that we did, so we said, if you want to get the characteristic polynomial, then the characteristic polynomial is found by getting the determinant of A minus lambda I. In this case, these are 5. And then what? X equals to 0, right? So using the same way that we did, so we have our A, which is this matrix, and then we have our lambda, right? So it is basically so to get a characteristic polynomial of E is equals to A minus lambda I raised to 5. And actually we're getting the determinant of this. So we're getting the determinant. So it is the same as determinant of A minus lambda I raised to 5. So using the same way that we just did previously. So it is just similar to, because this is like our A here minus lambda multiplied by multiplied by 1. These are 0, 0, these are 1, right? So when you put lambda here, then it will be just lambda on the diagonal. Now, when you come and subtract A, so it will be A minus that lambda, which is here, right? Yeah, so that is it. Yeah. Any other question? So again, when there are two eigenvalues that are the same, then you can just say, so just take one. If there are 3, then just take 1. And then you say multiplication. If there are 4, like that. So remark. The eigenvalues of a triangular matrix are exactly all the diagonal entries or the diagonal entries in the matrix with multiplicities counted. With multiplicities counted. So basically, in this case, we have 5 eigenvalues. So we also count the multiplicities. Okay, any question up to that? So let's come to the properties of the characteristic polynomial. So there is a very easy way of getting the determinant of a polynomial using the characteristic polynomial. And let's look at theorem 1.1, 2.1. If the characteristic polynomial, which is of that form, P is the characteristic polynomial of an n by n matrix, let's say A, then the phi, and then if we replace lambda by 0, then this is equals to the determinant of A. It is equals to the determinant. If lambda is 0, then it is equal to the determinant of A. So we can prove this, whereby we said the phi of lambda is equals to determinant of A minus lambda I, let's say IN, right? Let's say IN. Then if we replace this one, if we replace this by 0, so lambda, when lambda equals to 0, then lambda 0 equals to determinant of A minus 0 IN, right? So phi of 0 equals to, this will be 0, equals to determinant of. Now, if you look at this, if you look at this one, right? If you look at this equation here, if we replace this one by 0 here, if we replace this by 0, we are getting 0, right? Right? So we are getting 0. Like now, if you look at this, the diagonal, the leading diagonal here, there is a 0 here. Now, if you multiply everything here on the main diagonal here, it will give you what? It will give you 0. Basically, the determinant of this matrix here is 0. The determinant here is 0. Okay, let's look at an example. Example number 2. If phi lambda equals to lambda raised to 4 minus 3 lambda cubed plus 2 lambda square plus 5 lambda minus 2 is the characteristic polynomial of an n by n matrix A, then find the value of n and determinant of A. Find the value of n and the determinant. So in this case, the value of n is the degree of this characteristic polynomial. So what is the highest power of that characteristic polynomial? So the solution. So n is degree of the characteristic polynomial, which in our case here, the highest power of this degree here, of this characteristic polynomial is equals to 4. So n is equals to 4. So what is the determinant? The determinant is when lambda equals to 0, then determinant of A equals to phi of 0 in our case, which will replace everything where there is lambda here by 0. And we get what? We get -2. So determinant of A is equals. Now, if the determinant is 0, then it means it's singular. So if the determinant is 0, then it is singular. Let's look at theorem 2.2. If phi of lambda is the characteristic polynomial of an n by n matrix A, then A is an invertible matrix if and only if phi of 0 is not equals to 0. It's not equals to 0. So B of 0, like this one, is not equals to 0. So this basically is inverted. If it is 0, like what we saw in example number E, then it's single. It's single. Like for example, if we have phi that equals to negative lambda 3 minus 2 lambda square plus lambda, then when phi lambda equals to 0, then this is equals to 0. Equals to 0. So it is determined. So this characteristic, this the matrix which is on is giving us the determinant to be 0. So it means that that matrix A is single. So it's single. Any question up to that? Okay. So we say that 2n by n matrix are matrices. Let's say A and let's say B are similar if there exists invertible n by n matrix P such that B is equals to P A P inverse. So when we say two matrices are similar, if we have this matrix P and if this B is the same as P A P inverse, then the two matrices are similar as long as this P here is inverse. So this will lead us to the next section, which is diagonalization of the matrix. Diagonalization. But before that, let's look at a theorem here, which is 2.3. If 2n by n matrices A and B are similar, then A and B have the same characteristic. So A and B have the same eigenvalues with multiplicities counted. So the two matrices are similar if they have the same characteristic of number and they have the same eigenvalues with multiplicities counted. So we can briefly prove this. So we can prove. So we say that this matrix is similar if we have B to be equals to P A P inverse. So it is similar if we count as long as P P is invertible, as long as P is invertible. P is invertible. Then we also say the characteristic polynomial of B is the same as the characteristic polynomial of A. So to get a characteristic polynomial here, so we can say the characteristic polynomial, which is the characteristic polynomial of B of lambda, okay? The characteristic polynomial is the same as getting the determinant of B minus lambda I n is the same as getting the determinant of, right? Now we are saying that this B is equal to B, so we can replace this one. So this is also equal to determinant of P inverse minus lambda I n. It's lambda I. Okay. Now this IN, since or P inverse is in, if P is invertible, then P inverse can still give us what? IN. So it can still give us IN. So basically, this is the same as determinant of P inverse minus lambda P inverse there, right? So, okay. So let's. Now, this is also the same as we can factor out. So we can factor out P from this side. So P from here. So what remains here is A minus minus lambda there, right? Minus lambda. And then we can factor out P inverse from this other side, which is P inverse there, right? Right. So when you factor this one in again, then it is inverse. So since this should be a matrix here for this one to subtract, then basically this should be the same as there should be I. There should be I. So therefore, you can distribute the determinant. So it is the same as getting determinant of P, determinant of A minus lambda I n, and then determinant of P inverse. Okay. Now, again, the determinant of P inverse can give us what? So you can just combine this and this, which will give us the identity. So determinant of identity is what? Is what? So basically, what remains here is determinant of A minus lambda I n. And determinant here is the same as the characteristic polynomial of A, the characteristic. A. So basically, the characteristic polynomial of P is equal to A. So, yeah. Any question? So if the characteristic polynomial are the same, then they have the same eigenvalues. they have the same eigenvalues with multiplicities counted. All right. Now let's now come to the last section, which we might finish it on Monday, and then we do the review of your exam. So if you don't finish it on Monday, but I'm planning to set the exam from where we stopped up to section 4.5. Okay. So the final exam will cover section 5.1, 5.2, 5.3. But since it seems like it's what we have covered is so wide, right? Since the previous exam that we did. So I will set the exam 3 up to section 4.5. So from where we left, I think we left at section 2.9. Yeah, 2.9. I have already finished preparing the practice exam, so I'll post it up after the exam, after the class. Then you can go through it over the weekend, and then we meet on Monday and review it. Okay, let's look at section 5.3. Diagonalization. Diagonalization. So number one, powers of a square matrix. Powers of a square matrix. So let's look at definition. What is a diagonal matrix? So definition. So let's say 1.1 definition. A diagonal matrix is a square matrix in which all its of diagonal entries are zeros. The diagonal matrix, the square matrix, of all diagonal entries are zeros. So it means the main diagonal are not zeros, but the other parts are zeros. For example, let's look at example number 1. So we can call this diagonal matrix. We can name it as B, capital. So we can use the capital B to denote the diagonal matrix. So example number 1, find d raised to 2, d raised to 3, and d raised to k, where d is equals to -2, 0, 0, and 3, and k is a positive integer. So B is a diagonal matrix because the entries here are not zeros, but the entries which are not the diagonal in the diagonal are zeros. So what's up there and what's down here are all zeros. Now, what happens when you square d by d? So d is the same as d squared. So when you multiply the two matrices, which is -2, 0, 0, and 3, by -2, 0, 0, and 3, what do you get? What do you get? So when you multiply this, so this and this will give you -2 multiplied by -2, right? -2 multiplied by -2 plus what? Plus 0. right? The next one here will give us 0, and then this is 0. So it will be 0. The next one is 0, and this one is 0. It is 0. The next one is 0, and this is 3. 3 multiplied by 3. So basically, this is the same as -2 square, 0, and then 0, 3 square, right? So it is simple. So -2 square is the same as 2, and square is the same as 9. Now, what happens when it is now d cube? Sorry, d cube, which is the same as d square d, which is the same as d square, right? So we've already gotten d square here, which is that. What about when you multiply with b again? So we have our d square there, which is -2 square, 0, 0, 3 square. What happens when you multiply again by -2, 0, 0, and 3? What happens? So again, when you multiply this, so it is the same as this and this, which will be -2 square multiplied by what? By 2. Since the other one is giving us 0, so it is +0. The next one is this and this, which is 0, this and this, which will give us 0. This and this, which is 0, and then this and this, 0. And then lastly, this and this is 0, plus this and this one is 3 square multiplied by 3. Finally, this is the same as -2. There are how many of them? So sorry, this is -2. -2 there. So raised to 3, 0, 0, 3 raised to 3. Right? So you can continue like that. So basically, if this is cube, then it means that to cube is lesser than this. If it is square, this square, then you just do what? You just square those values here. So it's square. If it is cube, then to cube. Okay. Now, if it is now d, if you continue like that, if you continue like this up to d raised to k, right? D raised to k, then what you get is -2 raised to k, 0, 0, 3 raised to k. There. So that is what you do. Any question? Now, let's look at a theorem here. Now, if A is equals to P D P inverse, and we said if A is equals to P D P inverse, then it means A and B are what? They are similar. So this is A and this B are similar. So if P is inverse, if A is equals to PDP, PDP inverse, where D is an n by n matrix, and P is an n by n invertible matrix, then AK equals to PDK P inverse for any positive integer. Now, if this A and B are similar, and this B is the diagonal functions, then it means this A is also the diagonal functions. So if it is like that, then a raised to k or a raised to p, a raised to 3 is similar to p raised to k, p raised to 2, p raised to 3. So let's prove this. So let's prove. So we've said AK equals to PDK, P inverse. We want to prove this. So we want to prove this. So we know that AK is the same as A multiplied by A multiplied by A multiplied by A. And we have N copies. Or K copies of A. K copies of A. A is equals to A times up to K. Now, we know that A is the same as PDP inverse. A is the same as PDP inverse. Now, let's come and let's whether it's A here. The PDP inverse. So then AK equals to PDP inverse multiplied by PDP inverse multiplied by PDP inverse, and then you continue like that, PDP inverse, PDP inverse. Okay, K. Okay. So this is A, this is A, this is A, this is A. Now, so this is similar to PD. Now, this, look at this. P and then P inverse P, right? And then D here. We have this P inverse P. And then D here. P inverse. There is another one, P here. You continue like this. There is this P here. D. P inverse P here. And then there is a D and then P inverse, right? The last one. Now, P inverse P is the same as what? Identity. So this is P D I. If it is this is N, it is N by N matrix. D I N D P inverse, which will still give us I N. So basically, you can say this one is I N here. You continue like that, D, and then I N, and then D, and then we have the last one, P inverse. Inverse. So D, I N there, it will still give us the same thing. So this is the same as P, D, 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 and then D, and then P inverse. So how many copies of D here? K copies. So basically, this is the same as P dk P inverse, which is the same as what? AK. Right? So this AK is the same as P dk. Any question after that? Okay, let's look at example number 2. Example 2. Let A to be equals to A 2B minus 2A, then 0 and B, and then our P equals to 1, 2, 0, and 1. Then our D equals to A 0, 0, and B, where A and B are scalars. Where A and B are scalars. Now, number A, show that A equals to PDP inverse. Show that A equals P. We have our N here of P here. What we need to do is we need to get the P inverse. So we need to find the P inverse. Then P inverse is the same as determinant of this P is what? Is 1. So 1 over 1. And then since this is a 2 by 2 matrix, you switch. So it is 1 minus 2, 0, and 1. So that is our P inverse. So you switch this. And then multiply 1 time. So we have that. So we know that A is P, the P inverse. So we have our P, which is 1, 2, 0, and 1. And then we have our D, which is A, 0, 0, and B. And then we have our P inverse here, which is 1, negative 2, 0, and 1. So let's solve this to see whether it will give us A. So we can multiply the two of them first, which will give us what? This will give us one of these is A plus this is 0. This and this is 0, and then this and this is 2B. And then this and this is 0. This and this is 0. This and this is 0. This and this is OB. And then now let's multiply by this. Multiply by 1 minus 2, 0, and 1, which will give us what? This and this is A plus. So it is A plus. Okay, so this and this is A, this and this is 0. Okay, this and this is minus 2A, and then this and this is plus 2B. And then this and this is 0, this and this is 0. This and this is 0, and then this and this is B. Right. So basically, it is the same as. So you can just switch this. So A, 2B minus 2A, and then 0, B, which is equals to what? Which is equals to. So it is the same. Now let's find AK. So what is AK? So what is AK? So we know that AK is the same as P D K P inverse. Okay. So that's 1, 2, 3. So then this is now equals to is equals to 1, 2, 1, 0, and 1. That is for P. And then our D is A, 0, 0, and B. So basically, and we said DK is the same as A raised to K here, 0, 0, B raised to K there. And then our B inverse is 1 minus 2, 0, and 1. And then you multiply. So when you multiply, you should get the same thing. So since this AK is similar to DK, so it means that AK is also a diagonal matrix. So basically, when you multiply by AK there, so we multiply this, so we get, this is AK here, the other one is 0, this is 0, and then 2BK, the other one is 0, then this is 0, this is 0, this is 0, this is BK. Again, when we multiply by 1, -2, 0, and 1, then it is equal to, this is AK minus 2AK, and then plus 2BK, 0. This 0, and this one is 0, this is 0, and this is BK there. So basically, this is equals to AK 2BK minus 2AK, then 0 BK. And this is AK. Example number 3. Use the decomposition A equals to PDP inverse to find all the eigenvalues of A, where A equals to 4, 0, -2, 2, 5, 4, and then 0, 0, 5. Or P equals to -2, 0, -1, 0, 1, 2, 1, 0, 0. And our D equals to 5, 0, 0, 0, 5, 0, 0, 0. Use the decomposition to find the eigenvalues of A. Now, so in this case, A equals PDP inverse. We know that if A is equals PDP inverse, then A is similar to what? To D. If A is similar to D, then they have the same eigenvalues and they have the same characteristics for D. So what are the eigenvalues of D? So they are 5, 5, and 1. So basically, the determinant here, so we have lambda. So we can say A and D have the same eigenvalues with multiplicities count. Then eigenvalues of A are, so we get it from this D here, lambda 1 equals to 5 with multiplicity 2 and lambda 2 equals to because to get the characteristic for the lambda here is 5 minus lambda, 5 minus lambda. 5 minus lambda, 3 minus lambda, 4 minus lambda equals to 0. Characteristic 0 product 5 minus 1 equals to 0, 5 minus 1 equals to 0. So that one equals 5. With multiplicities 2, number 2 equals 4. Okay. So that's how we get it. All right, we will meet on Monday. So I will since I want to grade only one homework, then I will add some homework for the homework which was supposed to be due today. So you can submit it next week for Wednesday. Okay. So if you have any question, I have my office hours, which are always open. I've never seen anyone come. Please come. I'm always around. So you can email me or you come to the office.